Well, thank you everybody for joining here. I'm Tim Winders. I am a PhD candidate in technology, leadership, and innovation. Thank you for joining me today for my dissertation defense, a comparative analysis of dual credit and university students in subsequent university courses. Today's agenda will go through my research interest here, a very brief background discussion about dual credit and into the research questions for this dissertation, along with defining the assumptions, limitations, and delimitations of this study, and then a deep dive into the methodology and findings of this study, and then finally the results and any discussion that we might have. If you have questions during the presentation, feel free to ask me during the presentation, or you can save questions till the end. We'll do it both ways, however you're most comfortable with. So first, what is dual credit? In the state of Indiana, dual credit has a legislated definition, and that is a course taught by a high school faculty member, a college faculty member, or a college adjunct faculty member, where a high school student may take to earn both high school and university credit simultaneously. I have been very passionate about dual credit for more than 25 years. I worked at a community college for 20 years in the state of Texas, and there was a very robust dual credit program in the state. And so I worked very closely with our admissions team, our registrar's team, to improve our processes on the IT and technology side, to bring in those students, to make them feel like they're part of the campus, and really integrate dual credit into what the college was offering. And so when I came to Indiana, noticed that it was quite a bit different. In Indiana, while dual credit has been around for a long time, in 2011, the state changed the dual credit program and mandated that every high school in Indiana offer dual credit. They were a partner with a college or university to offer that credit, but we saw a significant uptick in the number of students taking dual credit courses starting in 2011. At that time, we also became concerned with credentials of faculty, both at the university level, but primarily at the high school level. In Indiana, the accrediting body for colleges and universities is the Higher Learning Commission. And the Higher Learning Commission sets standards for accreditation for credentialing of faculty. And that is, the faculty must have a master's degree in the subject that they are teaching, or a master's degree plus an additional 18 hours of credits in the subject that they teach. And there's a big concern that the high school teachers did not meet that credentialing requirement. So they were teaching dual credit for students to receive university credit, but didn't have the credentials to do it under the accreditation. And so a process was set out and a lot of discussion around the state of how to fund these teachers to get their credentials. Would universities and colleges still partner with these high schools and teachers to make it happen? Most colleges and universities provided a grandfather period where they would continue to work with the teachers at the high school until they were able to get credentialed. This did not happen at Purdue Northwest. There was significant discussion among faculty senate where the faculty around the table would talk about their experiences with their dual credit students in the class, or once students that had taken dual credit were university students. And there was a lot of conversation that they just said these students weren't ready for our classes. And instead of grandfathering these classes in, they cut off relations with any school or any teacher that didn't have those classes or those credentials. So dual credit enrollment at PNW started to drop off precipitously. And so this concern by the faculty saying, hey, these dual credit students that took dual credit, they're just not ready. and HLC saying, hey, they need to be credentialed, it got me thinking, are dual credit students ready? And while there's significant literature that tells us dual credit is positively associated with college attainment, with persistence, graduation, overall success, there is a lack of literature that talks about, are students ready for that first class when they come out of high school into the university? So that's what this study looks at. And specifically, the study was guided by 3 research questions. The first one, do dual credit students have the same grade in a subsequent university course as non-dual credit students? And then, is there a difference in student grades in the subsequent university course based on observable characteristics, the data points that we have in our student information system? And then finally, is there a difference in student grades in the subsequent university course based on the course subject? So do we see any differences with these? With this study, we do make the assumption that dual credit courses are of the same rigor and quality as university courses. The study is limited to the fact that we're using data from the student information system at Purdue University Northwest, and we're not including any non-observable characteristics such as student motivation and maturity in this. Those are not recorded data points in our student information system. Additionally, we're not considering instructor credentials. While that question really spurred my interest in this, that's the evaluation of instructor credentials is not part of this study. The course content is not studied. Again, we make the assumption that the courses are the same quality and rigor. And then finally, socioeconomic status is not included. This is a data point that is of interest. There is literature that says students that are of higher socioeconomic status achieve at a higher level. However, recent guidance by the Department of Education restricts the use of financial information for research purposes. So it's not able to use this data for research, even when that data is anonymized. This research study is a quasi-experimental study using secondary data analysis. As I mentioned, the source of data is the Purdue University Northwest Student Information System, bracketed by the years 2011 to 2021. So we've got a 10-year longitudinal study here. Again, we started 2011 because that's when we saw a huge increase in the number of dual credit students that came into the program. And 2021 is the last year for students to complete a subsequent course in order to collect data and complete this study. Dual credit students are defined as those students that take a course while they're in the high school, and university students are those that take a prerequisite course. University students are those that take a prerequisite course in the university. Later on, the subsequent course is when both the student type is taking that subsequent course in the university. So the dependent variable in this study is the outcome, and that is the grade in the student's in the subsequent course. We're using that as an evaluation of how well did they have learning in that first course. And the independent variables, the student status, the student sex, HUG status. HUG is historically underserved groups. First generation status, this is a student, the first generation in their family to attend college. The student's SAT scores, high school GPA, the subsequent course subject, and then I added in the time between courses to see if there's any time displacement or difference with the length of time between when students complete their coursework. Is that a contributing factor? So when we move into the methods, we first use data pre-processing for this. I use the techniques of data wrangling, where we really get a handle of and understand what the data looks like. We organize the data, visualize it in various different ways. The key step is going to be how we deal with missing data. I'll talk about that in just a minute. And then after the data has been processed, we're ready to analyze it. So the first step is to complete descriptive statistics. I won't review those today. They are in the dissertation. This gives an idea of what does the data look like from a descriptive perspective. And then the statistical techniques that were used in this study started with propensity score matching, and then finally with ordinal logistic regression. And I'll describe both of those in a little bit. So first, handling of missing data. It's important to understand that the best data is that is not missing. Anytime we have missing data, it lowers our quality. And any method that we use to handle missing data introduces bias into the study. In vogue, I say in vogue these days, is this computational technique using multiple imputations. This is the technique of taking your data set and replicating it for each variable where you have missing data. And then using a computational program to insert values into all the missing fields. And now you have n number of data sets, which you then analyze and combine the data and compare it later on. It's extremely complex and difficult. I did not use multiple imputation. MPA and missing indicator are also very interesting ways of handling missing data. In this case, they can both only be used when the treatment variable and the outcome do not contain missing data. So in this case, the treatment for us is the dual credit. We're considering dual credit as a treatment. So we know all of the student stats. We know whether they took dual credit or not. However, the outcome, that's our dependent variable. That's the grade in the subsequent course. In this case, we do have missing data. Because we're using the grade scale from the Purdue University from A+ to F as our numeric grade scale, we have a number of additional grades that were included, including withdraw, incomplete, pass, withdrawal while failing, and it's impossible to assign those a numeric value to understand what is the intention of the faculty member for giving this grade at time, what would have been the result. So those grades were treated as missing. So we don't have these other methods there. The most common and easiest to use method for handling missing data is complete case analysis, also known as list-wise deletion. This is where we only use cases or observations where every data point has a value that's complete in there. Everything else that has missing data, we toss out and we do not use as part of the study. So this study used complete case analysis to handle missing data. I want to show you, this is a table of what missing data looked like before and after. And I just want to highlight a few things for you. We'll talk about it a little bit later on. First generation status had a huge number of missing data. So if you look here, you can see in the dual credit students, there was over 20% of the dual credit students didn't report their first generation status, and over 35% of our university students didn't report their first generation status. So this is just a huge number that really, I believe, introduced some significant bias towards first generation status in this study. I'll talk about that a little bit more. So as we dig deeper into here, so we just looked at first generation status. I also want to point out these two subjects of economics and political science. While these are not technically missing data, they are cases where we had no dual credit students in that the 10-year time span that took economics or political science. So naturally, it would eliminate the university students that completed those subjects as well, because we didn't have comparison groups for them to compare. And I found this particularly interesting, the grade in the subsequent course. That's our dependent variable that we're looking at. That before handling missing data, there was a significant difference. We can see here a standardized mean difference between dual credit and university of 0.13, with the dual credit students having a higher grade. And then once we remove the missing data, it drops down to 0.03. So a very, very small difference. Dual credit is still higher, but very small. I found that interesting that you might want to, I wanted to point out to you. So before I get into the actual data techniques and statistical analysis, I want to share with you these two quotes that really rung true to me. As I was discussing this dissertation with a friend of mine, Dr. Ryder, I said, well, if any of the committee members asks you, well, why did you use ordinal logistic regression? You say, well, as you know, the data dictates the method. And it was sort of a tongue-in-cheek way to sort of bypass the question without answering it while saying, yeah, that's really true. And I share it here because that actually happened in my study. I changed the statistical analysis a number of times because the way I was looking at it didn't work. And Dr. Kuhn is quite familiar with what happened there. The next one, Dr. Peck here, shared with me, hey, if you have enough data, you can reject any hypothesis. And this reminds me of the adage that we've got, lies, damn lies, and statistics, because we can manipulate the data in a way to get us to the result that we're hoping to find. And I share that because as I moved through some of these statistical methods and changed how I was looking at this, it almost felt like data mining, like I was trying to get something. I was trying to get to a specific result. In this case, the result I was trying to get to is a valid finding of the data and the method that I was using. So these really ring true to me as I was going through this study. So let's get into some of this. Why propensity score matching? When a researcher sets up an experiment and you're looking at a treatment, you will identify your treatment and control groups and pick, let's say if we're doing something on human studies, I'll pick somebody that has specific characteristics and traits and give them the treatment, and pick somebody that looks very much like them and put them on a control group. And I'll keep doing that until I have a roughly equal number of treatment and controls. That way I can compare them afterwards. Well, this study is secondary data analysis. I'm not telling students to take dual credit or not take dual credit to see what happens. It's something that students do themselves. And so propensity score matching is a statistical technique that we can use to help create balance and eliminate the self-selection bias that we often see in secondary data analysis, where we're analyzing after the fact. The point and the idea of propensity score matching is at the end, we will end up with two comparison groups that are very similar to each other that we can then perform additional statistical methods on to understand, all right, now that we've got like comparison groups, what do they look like? So that the process for propensity score matching has three high-level steps. The first one is to estimate their propensity score. In this case, we use a logistic regression where we use the student type as our dependent variable. So dual credit or not dual credit. And then we regress on all of the additional variables in the equation, not the one in our primary question. We're looking at the grade, but all of our other variables. And the output of this regression is a propensity score, or a probability that that case, that observation, that individual received the treatment or not. Right? So that value is saved for every single one of those. Once we complete that, we then choose a matching algorithm to create our balanced sets, and then go through and estimate the impact with some additional statistical analysis. So there's a number of ways that we can choose, or the number of different matching algorithms. I looked at two in this study, settled on one in the end, which I'll talk about. The most common, easiest to use and understand is nearest neighbor matching. This is where we will just simply look at our data at the propensity score, the probability for it, and I find my first treatment individual, look at their propensity score, and then look through the rest of my data until I find a control person that has a very similar propensity score. I pull them out of my group and I say, okay, boom, that's my first sample. And I continue with that until every one of my treatment have been selected. Now, in this case, it's possible there won't be a control to match up with every treatment. If there's just not something that looks like that, we won't have that. If we end up with an output that doesn't have enough controls, then we can do with replacement. What with replacement means is when I pull the treatment individual out of the matching set, I leave the control in there so that that one control person could be matched with multiple treatments. So I end up with higher observations. There's other things that we can do, such as instead of 1-to-1, we can do 1-to-n matching, where I might pick one treatment and match it with up to 5, 10, some other number of controls, and then do that same with and without replacement. The next is more complicated to understand, but is pretty powerful, is inverse propensity weighting. And there's two methods that I looked at here, the average treatment effect or the average treatment effect among the treated. And so what this does is we calculate a weight for each individual based on a propensity score. With the ATT method, I assign a 1 for all of my treated individuals. All right, so they're not weighted. You see that's in this table down here. We see all of my individuals get a 1 for the weight, and then I weight my control cases with the formula of the propensity divided by 1 minus the propensity. What this does is it tends to weight those cases that have a very small propensity score. So in the sample down here, its propensity score was 0.05, meaning they're they do not look at all like a treatment individual. Their weight would be 0.05, very low. But if they're very heavy, if they look 0.95, they look very much like a treatment person, they get weighted very heavily. That's ATT weighting. ATE is we weight the two different groups inverse to each other, and with the idea of trying to make everybody look like they're treated and bring everything to the mean. The power of inverse propensity weighting is I use the entire set, the entire population that I have, instead of creating a sample from that population. With nearest neighbor matching, I'm naturally tossing out and excluding some number of control cases. They will not end up in my analysis. With inverse propensity weighting, I use everybody. Everybody's used in there, and then we can use the weights with any statistical method that will accept weighting on that method. So once we do all the weighting, the next step is to you'll really look at the balance of the two different sets that we've created. Here's a sample balance table, and what I want to point out is this column here, Cohen's d, or the standardized mean difference. And what you can see is between all of our variables, the absolute standardized mean difference between all of them was 0.3 before matching. So a medium a difference that was there. After matching in this one, this happens to be the matching table for 1-to-1 matching without replacement, we see 0.08. What we're looking for is a balance where our difference is as close to 0 as possible. All right, certainly less than 0.1, but as close to 0 as possible. There's some things that you can do to try to improve your balance, such as looking at quadratics and running your regression again. You can look at any interaction terms and run your regression again. In this case, I looked at all of that and nothing got the balance better than where we're at. If we look here, one concern is the high school GPA did end up at 0.15, but it's the best that we could do in this matching. So I went ahead and at first used all of those. I created 4 different data sets and looked at all of those to then estimate the impact, answer the research question. Is there a difference? So typically, just in a simple question, we might use a standard t-test just to see is there a difference between these two. And we had a lot of additional variables. So naturally, what I wanted to do was look at multiple regression. And the idea with the multiple regression is that it's very easy to understand. In a multiple regression, you have a linear relationship between your independent and dependent variables. So what this means is the equation that I get from building the model, I have a very specific coefficient for every variable that tells me what the relationship is with that variable and the output. So I can look at that very easily and just know, is there an impact or not? And then I've got significance with the overall model and significance of each individual variable as well. But I can look and see right there. It's easy to understand. It's commonly used. It's easy to interpret. One of the requirements with using linear regression is that you have a continuous dependent variable. Now, what I talked about, the dependent variable in this study is the high school GPA. And we know that it is very specific values along a scale. And in this case, there were 12 values in that high school GPA. And there are some studies that say you can use a distinct value variable along a scale if you have more than 10 or so values. It can be okay. So start out looking at that. So I started with linear regression. And there's a lot of requirements and assumptions to successfully use a model built on linear regression. I'll talk about two that really created problems for me. The first here is the assumption of homoscedasticity of the residuals. So really what this means is that what we expect to see is the plot of the residuals against a predicted value. We would expect this plot to be a randomized scatter plot. And what we're looking for in there really is that the values are randomized across there, and we're not seeing convergence or divergence of those residuals. In this case, I don't know what we're seeing, right? So as a statistician, when you look at this, you say, this just makes me feel really uncomfortable because it's not what you want to see. And it wasn't until after quite a bit of thought that I realized that what you're seeing here are actual bands. And each one of these, what looks like lines of residuals across this scatter plot is a distinct value in the dependent variable. And the residuals track along the same line of that dependent variable. So once you understand that, you could look at this and say, okay, well, the distance between this first point here and here and this point here and here, the height is about the same. And I think you could make an argument that maybe I don't really see heteroscedasticity, but I don't know what I'm looking at here. So kind of put the whole linear model on edge, and then what really tossed it out is the assumption of normally distributed residuals. And if you're not a statistician, you could look at this and see, all right, well, I've got this plot of my residuals, and I see my normal curve that comes along here, and it's kind of normally shaped, and what we look for is mean somewhere around 0 and a standard deviation of somewhere around 1. It kind of matches that, but we see this huge tail of values down here on the negative side and a big chasm of nothing on the high end, and then of course these large residuals that come up around the mean. And so when you look at this, you say, all right, I could again make an argument. It's for social science, it's good enough. But by pushing forward a linear model here, I think what it would do is really create doubt and question around the significance of the overall model, and do the p-values that I've decided to pick, do they mean anything or not? And part of the problem with this is just because of the data that we have. This is a plot of the grade in the subsequent course, and you can see that grade is not normally distributed. Now, it's not a requirement for linear regression that the dependent variable be normally distributed. And of course, going into the study, there was no assumption and thought that we would have a normally distributed grade. But I also didn't expect it to be this lopsided, right, where we see almost what looks like a logarithmic scale with the significant number of A's and the grades just dropping off precipitously. So again, there's some techniques that you can do to try to transform the dependent variable, run your regression again to see if anything changes. But because this is so skewed in one direction, any transformation that happens to it just skews it in a different direction. There's really nothing that can be done to get this to be anything close to being normalized. I still did go ahead and look at all of this, and the R squared values of these models for the inverse propensity weighting were in like the 0.03, 0.04 range. So just the model was horrible for those, and even for the nearest neighbor matching, they weren't much better, 0.13, 0.14. And again, in social sciences, we say, that's pretty good for social sciences. If we can get to 0.3, that's fantastic. And we certainly want to have that in engineering or medical sciences. But for social sciences, we have a lot of unexplained variables. So in this case, with some guidance and advice, toss the whole model out and start it over. And with the advice of looking at ordinal logistic regression. And this is key because the dependent variable is an ordered categorical variable. That means we have a specific scale where the order is important. We go from F to A, 0 to 4. So that order is very important. Now we don't. Ordinal logistic regression is not used as commonly that I've seen. I'm sure there's plenty out there, not common as I've seen. And it's very complex to understand and interpret. We don't get a nice, simple association with what the variables have with what the output is. Instead, we get a relationship between the values of an independent variable and a value or a probability of a value in the dependent variable. So what that means is I'm looking at, I say there's an odds, or I get a probability of this value in this variable increasing or decreasing the value or likely to get higher or lower on the categorical scale, in this case on my grade. The key assumption in ordinal logistic regression is the assumption of proportional odds. This is a little bit complex to explain and understand, but what it means is through every value of my variables, the odds for the change in the dependent variable are the same. Okay, so if I were to look at a population, I would say that the odds, and let's say I look at sex, for example, the odds of females getting a better grade than males is this percentage, and that will stay the same through every value that we look at. It doesn't change based on other factors or variables. So the odds of female getting a D or a C or a B or an A is the same across all of those as a male. So that assumption of proportional odds is really important because again, the output is not a simple linear association. It's an odds of a difference between the values in my variables. So we have to meet that. The other one that became important is having a certain number, a minimum number of observations per category in categorical variables. So in this case, categorical variables We're sex, hug status, first generation, and most importantly, the course subject that the students took. What we want to see is at least a minimum number of observations, somewhere between at least 10 or 15 or so. If we have less than that, we need either get more data into our model, or we need to combine those categories so that we look at them in some other way. Combining them is not something I wanted to do in this study. In this case, as I was looking at the data, we have one subject, biology, that had a pretty low number of cases or observations. What would I combine biology with? Would I combine it with math and chemistry and say I'm going to have to compare STEM and non-STEM? I could, but I felt that would really take away from the significance of the findings. So I really wanted to have the subjects out individually. So, that's what I decided to do, is see what we can do here. So having those assumptions understood, I went through and looked at the different models to see what I might choose. So the first one I started with was our one-to-one matching without replacement, and I saw too few observations with biology. So then I looked at one-to-one with replacement. Okay, I had more observations in there, but when I looked at the assumptions, that model did not meet the assumptions of the need. I had already, by this point, discounted trying to use the models that use the inverse propensity weighting. The balance on those models were just not good. They weren't much improved over the unmatched models, and so I discarded those models and just stayed with nearest neighbor matching. So first step then, but I didn't have enough data in the biology set, was to bring in additional data. So, okay, well, let's do a higher number of matching. And the proportion of the two groups was about 1 to 10 or so. I said, well, it seems like a good place I need to start. And so I did a 1 to 10 matching. So when I did the nearest neighbor matching, we would take each individual treatment and match it with up to 10 controls. And in that case, it matched everything and had huge numbers. Everything looked great until I ran the assumptions, and this model did not meet the assumption of proportional odds. And that is, as the different variables changed, we saw different odds happening to get different grades. And so it's like, okay, well, you could still use this if you were to change to a different regression model, such as multinomial. Multinomial, sort of a last resort, but you really want to use that when your dependent variable is not ordered. So if it's something like a state where you live, which it doesn't really have any specific order, because the output of a multinomial regression will tell me whether there's a difference, but it won't tell me a direction. It'll just tell me whether there's a difference or not. And I care about the direction. I want to know if there's a difference, are they doing better or worse? Not just, well, there's a difference, go figure it out. So that wasn't going to work. So then I stepped down to 1 to 5, 1 to 4, and then finally 1 to 3 was the highest ratio that met all of the assumptions of the model, and it included enough observations for me to move forward with it. So, we want to look at the same thing here again. I will highlight. You can see we ended up with 14 observations here in our biology. The same before matching, 0.3, and after matching in this set, son of a gun, was better than the 1-to-1, ended up at 0.07, and then our the GPA, which before I mentioned was 0.15, now it's 0.09. So everything is under 0.1. We have a good match. We have the data that we need. I have a solid data set that's going to be able to answer some questions. Let's zoom into a couple of variables here that were of interest. Sex. This is the only variable after matching that ended up with a worse balance after matching. You can see before matching, the standardized mean difference was 0.02, where there were fewer males in the dual credit population. After matching, 0.07. So it's a higher difference, and we ended up with more males in the dual credit population. The sign, the negative sign, indicates fewer in the dual credit in this case. So that's the sex. If we look at the grade in the subsequent course, again, we're not trying to balance on the grade. Just looking at this as an output of how did this perhaps do? So before matching, we saw a 0.08 difference where dual credit students were a little bit higher. After matching, minus 0.1. So the dual credit students are a little bit lower after matching. This one is huge. High school GPA, it changed significantly from 0.33 to minus 0.09. I want to highlight time between courses because I mentioned before we want to get our difference as close to 0 as possible, ideally below 0.1. Time between courses there's such a significant magnitude of difference between the two that bringing that difference together is statistically impossible. Because if you think about the way the courses are delivered and the way this variable is measured, so the time between courses here is a measurement of days from the first day of the start of their prerequisite course until the first day of the start of their subsequent course. Dual credit is very heavily loaded in junior and senior years in high school. So if you think about a student taking a math course in their junior year, they started in the first semester of their junior year, they may not take the second semester of that until perhaps the second semester of their freshman year, maybe the second semester of their sophomore year. So we see a difference with dual credit students between those courses of almost 2 years. Whereas at the university level, it's typically an average somewhere around a year, and we know many of them are much shorter, only a semester apart. So if you think about those numbers, the fact that we're able to get this somewhat close at all is interesting. And this standardized mean difference includes this time between courses. So it does not include the grade in the subsequent course because that's not something we're trying to balance on. But it does include this time between courses. So this 0.07 value includes that 0.56. If we were to remove that out, it dropped that standardized mean difference to, I think it was 0.04. So significantly smaller. So jumping through all these hoops, I return to these quotes. And I hope now you get a sense of why these were important to me and why the data dictate the method. In this case, it really happened. I jumped through all kinds of hoops because the data would not let me use a specific statistical method. And then, of course, Dr. Peck saying, if you have enough data, you can reject any hypothesis. Again, the feeling of data mining and jumping around between models and sucking in more data really felt like that could be a reason for what's happening. And again, in this case, just moving on with what's happened with what the data was telling me. This is what needs to happen. So that moves us into the results. And the results of the ordinal logistic regression tell me that so the significance of all of our independent variables here. What we see and looking at the p equals 0.05 level, that sex is statistically significant at the 0.004 level. We see hug status is again statistically significant. We see the high school GPA is statistically significant, and the subsequent university course is statistically significant. So these things, the model tells us, are all significant. We'll dig into what they are in just a minute. But notably, look at what's not. Student type is not significant. This model tells us that dual credit, non-dual credit does not statistically significantly predict what the output is going to happen, what they're going to get here. First generation status. This also shows, at the p equals 0.05 level, it is not statistically significant. That is not supported by the literature. Literature tells us that non-first generation students are going to do better than first generation students. This model says there's no significant difference. I believe that is because of missing data. Talk about it a little bit more towards the end, but that's a significant thing. Also point out that the SAT scores are just garbage. They are not significant at all in this output, but high school GPA is. And this supports, again, some of the literature that we're seeing and decisions that universities are making across the country of moving away from using standardized test scores for admission into programs and looking at the high school GPA only. This output here doesn't tell us which courses are significant, but it just tells us that the courses are significant. So let's dig into what those mean. This is the garbage that SPSS puts out. It's a huge a table that gives the parameter estimates for everything we're looking at. And I've highlighted a few things here for you. If we look, you can see over here, it tells us just for example, student type 0 or 1. I added in with the coding what those meant, dual credit or university, and then a couple of other samples, the sex, and then I picked out one of the courses. What's interesting and important, and this table really demonstrates, is when you're doing a linear regression, if you have a dichotomous variable, the linear regression is always going to give me the output for what you coded as a 1. And if you code it as a 0, then the coefficient is just 0. It doesn't matter. It's always a 1. In an ordinal logistic regression, the value of your categorical variables is not used. It's not part of the equation or the formula. And you can see this if you look at student type. For example, in this case, I have the student type of 0, right? University. It's the one that has the values on it, and the one with dual credit doesn't have values. Not what you would see in a linear regression output. Okay? This is what just us telling us that the one category in that variable is being compared to the other category in that variable. So the reference category is the one that doesn't have any numbers on it. So again, if we look at the output from our student type, it tells us in the significance column, this output is not significant. 0.221. Okay, the dual credit is just not a significant predictor. But if I look at sex, I interpret this row in such a way that it tells me, again, I look at the significance and I see that that the significance for sex is 0.004, and it tells me the output here 1.286. What this is saying is that females are 1.286. They have the odds. The odds of females getting a higher grade in the subsequent course is 1.286 times that of a male, or 28% higher than what males get. But I really want to show you the high school GPA, because it blows my mind how significant this is. When you look at high school GPA, it's extremely significant, and the odds. So what this is telling us here, because high school GPA is not a categorical variable, we're treating it as a continuous variable, that for every 1 unit change in that variable, we see a 3.999 chance of them getting a higher grade. Or if a student moves from a 2.5 GPA to a 3.5 GPA, there's a 300% chance they're going to get a higher grade in the subsequent course. It's just outstanding. The high school GPA is the single significant predictor of student success. And then if we look at one example down here, mathematics, I pulled this one out because we see a number in the v exponent value of less than 1. So what this is telling us is, again, we compare all of these courses. They are 1 through 8 In this model, I entered them alphabetically, so the reference one, number 8, was Spanish. What this is telling me is that mathematics is significant, and students in mathematics have a 0.325 chance of getting a better grade than students in Spanish. In other words, it's a lot harder to get a better grade in math than it is in Spanish. And do that for all the variables, interpret them all. And oh, by the way, I've got 8 different courses, so we run this model 8 different times for every course, and then we can answer all the research questions. So let's dig into it. First one, we started out this study. Do dual credit students obtain the same grade in a subsequent university course as non-dual credit students? And this study showed that student type was not a statistically significant predictor of grades in a subsequent university course. Could stop there, because everything else I was thinking about, if there is a difference, then do the other things matter? In most cases, they don't, but I have all the data, so let's answer the other questions as well. So as we look at observable characteristics, sex, yes, sex is significant, and the odds of females to have a higher grade in subsequent university course is 29% higher than males, 28.6% higher. Hug status, 39% higher for non-hug students. This is telling us that there's a pretty significant difference between students that are historically underserved groups. So we get back to first generation status. Again, this study showed that there was first generation status was not a statistically significant predictor of grades in the subsequent course. I mentioned it before, I'll say it again. I strongly believe this is rooted in the fact of missing data. The literature tells us that first generation students struggle, have a harder time, need more assistance than those that are not first generation. Logically, it makes a lot of sense. And I think that this is an area that we as universities can do better at educating our students. What does first generation mean? Why is it important for you to share and disclose that information? And areas where we can put resources to support students that have demonstrated through literature and perhaps our own data of making a difference. However, a third of the students in the university population just didn't report this information, and so it ended up that in this study, first generation status was not statistically significant. SAT scores, nope, not at all. High school GPA, I already mentioned it, huge, and it makes a lot of sense that in this case, when we're talking about academic performance, previous results are the best predictor of future performance. And I think this really supports the move that faculty have made recently to eliminate SAT scores as for admission requirements and placement, and really look at high school GPA. It made such a difference in the prediction of student success. High school GPA is the single largest predictor in this study. And then finally, I mentioned before, time between courses, just not statistically significant in this study at all. So that gets us to our subsequent course. Does it make a difference? I already mentioned we had 8 courses that you saw on the screen. And so the 7 are compared against the 1 reference. We build a table for that, and then change the reference group, run it again, build the table, et cetera, et cetera, et cetera. Do that a number of times until we have all the results. And then I put it together in this fancy chart that we see here. So this chart, we can read it across in our row to say, all right, this is the course that I'm interested in, and then read it down to see how does that course compare with another subject. So if I were to read across German and then down mathematics, I would say, students taking German have the odds are 9.326 that they're going to do better than mathematics students, or they have an 800% chance of doing better than students in math. If we look down here at the bottom, we looked at before on the other table, mathematics and across the Spanish, I see the same 0.325. we can look at it the other way around and say, oh, okay, somebody doing worse, it's hard for me to kind of think about. So let's say Spanish compared to mathematics. And I can see students in Spanish have a 3 times chance of getting a better score than mathematics, or over 200% chance of them scoring better on the subsequent course than students in math. So these are ordered, the rows subjectively from, I'm going to say, easiest to hardest, with German being the, in this study, the easiest, mathematics being the hardest. You can see that in this far right total odds. I just labeled total odds 4. So how combine all those, what, 4 getting a better grade. And this bottom row, the total odds against. So in this case, on the odds against, the higher the score against, the harder the course. And in the rows over here, the higher the score, the odds for, the easier the course. In this table, the ones indicate that there was no statistically significant difference between those courses. So the odds ratio is 1, or 0% chance that there's a difference between the 2 courses. And this, describes all of the courses in detail. And I think this table supports my earlier decision to say, I don't want to lump in biology with chemistry and mathematics and call it STEM. Because look here, biology is right in the middle. And I see that it's 3.389 against chemistry and 3.977 against mathematics, and basically no difference between the others. So if you were to just arbitrarily, right, as a researcher, lump in biology in this study with chemistry and mathematics and call it STEM, I think it could have made a difference in what course subjects would be statistically significant and in what way. So breaking them out this way, to me, really illuminated, what was there. That answers all of my research questions. So now it's to you. What questions do you have of me and of this study? And thank you for all listening very much. I appreciate it.
Great, thank you, Tim. Questions that you might have? I'm going to start.
Okay.
Go back to that prayer table.
This one.
Yeah. So why do you have total odds for and against, as a number? Is it truly additive if these are all?
Not necessarily. It was a way for me to help visualize and look at what. Again, I said subjectively, German's the easiest and math is the hardest. So I don't have any literature that says, yeah, they're additive or they work this way. Yeah. To me, this is more of just a visual representation of what the courses, how they relate to each other. Yeah. And in the paper, I present this information in several different ways, just alphabetically, so you can see what they all are, and with a plus and a minus, whether the odds were for or against each one. I include the odds ratios, and then I sort it. Okay. For me, this table gave me the best visual representation of what was perhaps hardest or easiest.
Mm-hmm. Okay. I don't know. Because I might look at that and I'd assume that it's additive when it may not necessarily be.
It may not necessarily be.
Looking at two-way tables like that, that's what the mind is trained for. So,
right. And so.
But is this table actually in your?
It is. It is right.
Yeah.
This is in the paper.
Okay. Well, I'm agnostic about whether you leave it as is or not.
For me, again, it's simply a visual representation, and the table with either pluses or minuses, or the numbers without the sum and ordering, is an accurate representation of the odds ratios between each courses.
Okay.
Any questions online?
Did you think of like, could you go back to the table where you had all the walls type 3, and you were giving the significance?
This one?
No, the one before.
This one.
Yeah. So like, what was the overall fit? This is like the fit of each of the individual.
Fit of each of them individually. The odds ratio, unlike a linear regression, doesn't give you a equivalent like R squared fit for this. There is a different fit in the paper that was included to show what the overall fit was, and it showed that it was significant.
Like deviance or whatever it's
exactly
called.
right. Yeah. That's not a presentation. It is in the paper.
So, and I remember it was like just humongous.
Yeah,
like,
I think it was even less than 0.001.
Yeah.
I think it was significant at that less than 0.001 level.
Is it possible to, I mean, okay, not saying overfit but get rid of the non-significant variables there and kind of see if you could pare it down to, not suggesting, I'm just saying maybe for future work, pare it down to just a model that fits the data on the one hand, but on the other hand, all of the elements are also sort of like significant.
Right. So create a model that only uses variables that contribute statistically significant to the model.
Yeah, and then you might see some of these profoundly significant ones not so significant. Get a little bit better for future work. I'm just saying.
Thank you. Yeah, I think that's definitely possible. If we look at it in different ways, bringing in perhaps handling first generation in a different way as well, or someone can't collect additional data in future study for that type of looking at it that way. What I will say is that my primary interest in this model in this work was looking at student type. And this model showed that student type is not significant. Valid or not, questionable or not, all of the regressions showed that student type was not statistically significant. If we do a simple t-test of the balanced groups, the student type is not statistically significant. The only time that I can show where the student type is statistically significant is if we do an independent samples t-test of the original data that includes all the missing data and everything. Then the student type is statistically significant, with dual credit students getting a much higher grade in the subsequent course, which makes sense because of the natural self-selection into dual credit by higher achieving students and overperforming students. So we would expect to see that, and that's why the propensity score matching and creating balanced groups is so important. I will say though, even if you look at that original model and the original data, if you do a regression on that, again, I didn't get the same problems with meeting the assumptions of that model. It comes out and student type is not statistically significant in that model. As soon as you start adding in any additional variables, student type immediately says nope, it doesn't. It's not statistically significant.
I know when you're talking about the multiple regression there, I didn't realize this till you were talking right here that. It was, and it made sense to me that you had said that it didn't give you a direction on the, increasing one variable, decrease to increase the other one.
Right.
But it wasn't in your thesis. And yet other parts, like you were talking about the difference between nearest neighbors and the inverse propensity, you did talk about the alternative methods that you had used. Was there any reason why, like you discarded, like you said, you talked about these different models, and yet sometimes you put it in the thesis and sometimes you didn't? Was there any reason why you didn't do the multiple?
I mean, at that point, in the thesis, I only described the 1 to 3 matching in the actual data. I described the possibility of using other matching methods in the thesis, but I don't talk about how I actually did it. And so in the document, that's not there. Those additional methods. So I didn't talk about multinomial regression or linear regression in the thesis. Just like I used propensity score matching, and I talked about how you could use different matching methods, but only gave results of using one. And I think what you're asking is, so why didn't I talk about I could have used multinomial or I could have used linear regression at that point? It didn't flow. It just didn't feel right.
No, I think that's.
So that's why I didn't. That's why I put it in. It just didn't feel. It didn't feel good.
I have a question in the comments. If you could see it, let me bring it up. It says, for the table near the end, did you happen to take a look at the weighing for major versus non-major students taking the course?
No, student major was not in as part of the variable set.
Yeah. I had a quick question too. Go back to the table on HUG status. So you can't get at socioeconomic information.
Correct.
Because what's your thoughts on the relationship between those two things? I mean, you get on
I think they're probably related,
Yeah.
And other studies are starting to get around that, doing using different proxies for socioeconomic status, such as zip code for the address. I think that's problematic in of itself, and there's a lot of literature that talks about the pros and the cons of that. And I think at this point, our best options until the Department of Ed changes their guidance is to look at research pre-NIAP 2017. That really shows us what the impact of socioeconomic status is on student outcomes. Right. So really, my conclusion is that we know what's statistically significant. We know the things that impact student success. So as legislatures, as administrators, as universities, we really should be investing our dollars in those areas where research, not just this study, but other research has demonstrated students need help, or we could potentially make a significant impact. It doesn't make sense to me to try to invest in areas that there doesn't seem to be a problem today. If there's no problem, or there doesn't seem to be a problem, or this study says there's no statistically significant difference in the outcomes between dual credit and university students, why put efforts in and money and time into some of these other changes if we don't know if it's going to make a difference?
Dr. Earth has a question when you're ready.
Great. Yes.
Marilyn.
Hey, raising the hand worked.
Yes, it worked. Great.
I just wanted to say exceptional job on the statistics and the presentation. Very well done. As the policy education person on the committee, your last mention there of where the legislature spends their money and so forth. What I'd like to see is not just this piece of research as a dissertation that goes into the archives, but for you to do something with it, for the Commission for Higher Ed to present it, to do some sort of a paper, presentation, white paper, whatever, to get this information across to them, so that it's a serious undertaking and costs a lot of money to require these teachers to go back to school, a lot of time and effort on their part. So if indeed it's not really making a huge difference, then it's something that the legislature should know and base their decision making on some solid data rather than what people think.
Yeah, just thank you. I appreciate that very much. And as the education policy person, there's significant controversy around teacher education and being able to provide the professional development to educators so that they can dynamically adapt to different learning styles in the classroom. And I think that's really the key, is being able to understand your audience and shift gears so that you can meet them where they are learning. Investing in that type of professional development, but the literature tells us that's going to make a huge difference. But simply saying, oh, you don't have a master's in mathematics, you can't teach mathematics. I don't know. Is that really, does it really make a difference? Or, you know, biology or whatever it might be. Does that matter? Well, this study tells us that there is no difference in the outcomes. Didn't look at, you know, teacher credentials. So I think that, you know, might be the next step for future
will be the next step, Tim. Yeah.
Future workout. Go out, and that would you know, mean going out and not just, you know, going to each school to collect the information, but getting their buy-in to provide that information, and that is politically a significant undertaking, but I think it's one that needs to be done.
By another PhD student.
Someone else.
Someone else. That's funny. Any other questions?
I do have a question. Thank you.
Yes.
Good job with your presentation and the thorough analysis. I know you have this on your dissertation document, but I'm going to ask it because you didn't really elaborate on the discussion and implications. So can you just recap very briefly where your findings align with previous work and how your findings contradict you know, what literature says about, you know, just in general about the findings?
Sure. So this table here is a good place to start. If we just start at the top, student type. You know, this study said, you know, there's no you know, significant difference between dual credit and university students. Now, that is answering this specific question of, you know, in subsequent courses. So it's the first course they take after the dual credit course. Previous research tells us that dual credit is positively associated with students just going to college, with them succeeding in college, persisting to graduation, getting jobs and being successful. The dual credit is positively associated with all of that. And so this study should not imply dual credit is not important. Just the opposite. This study says that dual credit is equal to, I mean, you can't really say that in a, you know, hypothesis, you know, statistical way, but really there's no difference. And so, you know, dual credit is important. This study confirms what previous literature tells us, is that in general, females perform academically better than males. That historically underserved groups perform lower than those that do not identify as historically underrepresented. Again, the literature, you know, tells us all of that. I mentioned before about first generation status. The literature does tell us that first generation status is important, and that students that are not first generation tend to outperform those that are first generation. There's you know, contradictory literature around SAT scores. You know, this study again tells us that it is they're just not statistically significant. We have, you know, a body of literature that talks about the biases that are in standardized tests and why they, you know, should not be used anymore. I think, you know, this study showing that based on students' SAT scores, we can't really predict what's going to happen with their outcomes. Goes to support the irrelevant nature of standardized test scores. Same thing with high school GPA. Is, you know, there's a body of literature that shows that, you know, students that perform better in high school perform better in the university, and that's clearly what this study shows. I do not have references or literature around any time effect or differences between courses, so I can't speak to whether what the literature tells us on that. And there is very little literature out there that talks about course subjects, most of it concentrating in the fields of mathematics on how we can improve the goals, that outcomes of students in mathematics, and whether there's a difference in various different teaching methods, or again, the credentials of the instructor. I referenced a fantastic study that I really liked by Carolyn West at the it was at the Naval Academy, where they looked at very specific courses in the Naval Academy, and this is where they came up with the idea that deep learning in those first courses, which is typically brought on by faculty that had PhDs or advanced degrees, resulted in better success in the subsequent courses. So their work is one that highlights where course, not just the course development, but the instructors made a difference on the outcomes in the subsequent course. So that's an interesting piece of work that if you haven't looked at, you're in the education field, would be worth going and reading. I think that type of study, again, there's a number that look at mathematics and how dual credit you might and has positively impacted students, specifically in mathematics, but maybe not so much in other courses, other subjects.
Thank you.
Thank you for the question.
So I've got two thoughts, and there's a couple little edits that I'll share with you afterwards.
Okay,
I think
perfect.
are too controversial, but the two thoughts that I've got, and the first one I want to build off these last two questions, because I think they're related here, and I also want to appreciate all the work you've done. I mean, you've got nearly 20 people here in the meeting to start with. That's probably the best I've seen ever. So you're on an interesting topic.
Well, thank you to my colleagues and family and friends that have spent the last hour
or logged into multiple
longer with us.
computers.
Or peers, right?
So nice work there. So the one question I think, I think this has some personal meaning to you, but what does it really mean? And this goes back to, I think, these last two questions. I don't feel like you end with a nice, strong punch, So at the end of the document, end with, why does this matter? And so I think you just talked through it. I also think that in section 1.1, you mentioned these literature-based concerns. Maybe go back and speak against them or for them, whichever one it is. And then in 1.3, you talk about the significance. And I think you could situate your findings in terms of that significance. And I don't know if this is something you need to answer right now. I think you just did a nice verbal, but I think that putting there at the end, so that the reader gets to the end of this and says, okay, there was no difference in subsequent course GPA, and therefore X, whatever X is.
Okay.
And you might have a biased opinion about which direction you think it should go based on your 20 years of experience. Others might have a different opinion. Doesn't matter. But what does this mean for them? So I think that's the biggest thing that would help. And related there, I don't know much about Purdue Northwestern. So if I'm trying to make decisions for a situation that I'm in, generalizability, how do I do that? So it might be helpful for you to talk somewhere, whether it's chapter 3 about a context or chapter 1, maybe about an introduction, talk somewhere enough that another, say a university in South Dakota, community college in Maryland, does this mean equal things to them? Or is it that your students are different? Are they primarily working adults or are they traditional college age? I couldn't quite tell, and therefore I wasn't sure how to interpret. So think about that generalizability. And I think that's related to, what's it really mean? So what's it mean for everyone? So that's the one thought that I had that echoes a little bit of the last two comments. The other thought that I had, and I think this goes back to what Dr. Kuhn was saying earlier, maybe this is the next paper. So be careful, but I couldn't tell how questions 2 and 3 added to your comparison of dual credit. So maybe they would have been exciting if question 1 had been different.
Exactly.
But I'm I'm just versed in statistics enough to be dangerous here, so
Okay.
take this with a grain of salt. But just because question 1 did not show a difference, I wonder if that means you couldn't have looked at questions 2 and 3 in that context. In other words, maybe question 1 wasn't different because of the way you set up the analysis. So, for example, I wonder how with, and I can't remember what questions 2 and 3 were at the moment. Oh, like females, for example,
right,
or non-hug students, for example. So would they have been different in this? If you had narrowed down to that group for question 1, would question 1 have been different? So I don't think you have to exclude that question. You see what I'm saying?
right, right.
And same with 3.
Yeah.
So I wonder if that's worth looking at later.
Well, so I did look at quite a bit of that. And as I was looking at, so this goes back to the linear regression. And so all the caveats around assumptions and validity of linear regression. But bringing in and removing variables as I looked at that model, running the linear regression at the highest level with just including student type, just the one variable. First of all, the R squared on that model was like 0.001. Okay, so that model describes less than 0.1% of the variability that's seen in the dependent variable. So that tells me right there that it doesn't fit at all, and besides that, it also said the p-value or the significance on that variable was like 0.997 or something. It's just completely irrelevant. You might as well just not even look at anything. So I looked at it that way. I also looked at it bringing just one variable at a time. And it started to make a little bit of a difference, but through all of that, the findings didn't change significantly. So some of these did move in and out of significance depending on what variables I included. And I did think about that, especially as Dr. Kuhn and I started talking about the concept of propensity score matching. And this study was looking at dual credit, right? And so if I wanted to look at, well, is there a difference, between males and females? Then I might have a study based on sex and balance my groups based on the sex and not worry about student type. Those are different studies, beyond that. And this is really in the context of balanced groups between dual credit and non-dual credit students. But this does generalize across the rest of the data set that we saw. Thank you. Look forward to your edits and or with Chad and with you on trying to bring in some of those other thoughts into those.
Yeah,
into those
I've been taking some notes.
And I'll package a couple things up in an email that are just less important right now.
Oh, thank you.
Perfect. That's great.
Appreciate it.
Okay.
All right.
Any other
This
questions?
ends the public portion of this.
Okay, that's it.
So,
No more questions.
Marilyn
Thank you, everybody.
and Allie, if you would stay on, and we're going to kick everyone else off. Thank you for your attendance today.
Thank you, everybody, for being here. I appreciate it very much. Your support has been fantastic throughout this effort.
Contact them for the
Thank you.
cliffhanger.
Cliffhanger. Okay.
All right. Thanks.
So, thank you all. Goodbye.